Hello, and welcome to Technically Speaking, a podcast where scientists and engineers come together to chat about a common interest, share knowledge, and satisfy some curiosity. I'm Laura, and in this episode, I'm joined by Ghinwa, Emma, and Clea to talk about how each of us learn to code and what we use it for. So, to start off with, Emma, can you tell us a little bit about what you're coding and how you got into it?
Yes, well, how I got into it, perhaps a bit different to how some people that I know got into coding. And that was because in my degree, we had a non-optional module in Python. I actually enjoyed that a lot more than I thought I would. And then I ended up taking another Python module in my second semester. And over summer, really got into just like looking into what the code can actually do. And in my third year now, I actually joined the Robotics Society. And I'm a part of a team that's trying to get a robot arm to play chess. We're working in MATLAB there, and that's like very new to me. But that's currently what I guess I'm coding on, as well as some like lab stuff, which I have to do, but mainly the robotics trajectory stuff.
Cool. So you're doing this for fun. Your degree is physics, isn't it?
Yes, I'm on an MPhys, and this is so third out of fourth year. And so I figured this isn't my final year, so maybe I can spend some extra time doing some coding for fun, where I don't like it doesn't contribute towards my grade essentially. So that's quite nice.
And that's quite a nice story about it, doing it for fun, but having learned it from your undergrad degree. My undergrad was physics as well, but it was a long time ago, and we learned Fortran, which is very different, I think. Clea, what about you? How did you get into coding?
I do the same degree as Emma. I also study physics. For me, coding was just very practical, and it became necessary at some point because in first year, so we didn't do any coding, and it just felt like, especially when we were doing labs, that there was a lot that we couldn't do, and we were actually stuck and not being able to do some things, not being able to present the data the way we wanted it to look like. So I really felt like coding and using Python could help me for that. Learning to code was actually my lockdown activity because I didn't know what else to do with my time. I started doing some online courses because there's just so much out there. So when I started learning Python, and then I took the same module that Emma mentioned that was mandatory for us. And I did really enjoy it as well. And now I just mostly use Python in my labs on almost daily basis, I guess. And my latest lab was on particle physics. And so we were just analyzing a lot of data using coding.
Okay, I feel like we'll get into a lot of the details about exactly what you're using it for and various other things as we get through this conversation. I really like that you're doing something that's mandatory but also enjoying it.
Yeah.
Ghinwa, I think your experience is quite different from Emma and Clea's, but I don't want to put any words in your mouth, so would you want to tell us about it?
Yeah, definitely. It wasn't a fun story like Clea and Emma because I had to do it in late during my PhD, during the third year. And whoever did PhD knows the stress actually of the third year during PhD. So I had a PhD project which was meant to be totally experimental. So I built a rig in the lab, tested at different operating conditions. But then I reach a point where I need to gain more understanding of the physics and science behind what I'm doing. And I need to predict results at different operating conditions. So I had to do modeling, and I had to start learning coding really in my late third year of PhD. But it was a very rewarding experience because it opened up a whole world for me, and it allows me actually to get the new job I'm going to be starting soon.
So I guess you had to self-teach yourself in your PhD to code, right?
Yeah, that's true. Well, I had first to gain the logic behind coding, which wasn't really the logic that we use in our day-to-day life, isn't it? To do that, I just had to break some link in my mind. So what I did is I had to watch videos every night before sleeping for 10 minutes about coding, whatever it is, Python or MATLAB, any language really. And then it seems like with time, I start to get the logic behind it, and I start to be more familiar with what we are doing here. And then I start really taking online training, self-teaching, and then getting on the track of most people do actually to learn coding.
Wow, that's so impressive. And the fact that self-teaching actually helped you in your career as well.
Oh, yeah.
Very cool. Yeah, and it sounds like there are some common themes there. You've all put the effort in to learn to code in your spare time, it sounds like. So I mentioned that I did physics as part of my undergraduate degree. It was a long time ago now. And I learned Fortran. It's mostly maths based. I didn't think much about it at the time, but maybe about 5 years later, I ended up doing a PhD, and I got that PhD position because I knew Fortran, and it was useful for the computational chemistry that I was doing in the PhD. But I think Fortran's very different to MATLAB and to Python as well. So I guess before we get into our discussion about what projects we're working on now and a few other things, it might make sense to explain what some of those differences is and how the coding languages work. So if I say that Fortran is maths based, it's quite simple. It's the only sort of inbuilt things it can do is like trigonometric functions in logarithms, I think, and exponents. But how does that compare to Python?
For like starters, I noticed what I found incredibly useful about Python when I was working on my lab in astrophysics was just you have a module called AstroPy, and it does everything you could ever want it to do in astrophysics. And the most important thing I found it did was actually like convert between coordinate systems, because I still don't really know right ascension, declination, and latitude and longitude, but you don't actually need to know it. You can just use like the inbuilt functions. And in MATLAB as well, I've noticed already there's loads of like inbuilt things you can like install as well, specifically for robotics and like statistical maths like modules you can install, and you can use them to generate random numbers, or you can use them to model different systems. And it does kind of a lot of the work for you. And it's like mainly just adapting what's there to what you want it to do. Python and MATLAB are probably a lot more similar to each other than Fortran is by the sound of it.
Probably. Fortran might have changed since I first started using it. I think it originated from like 1977, and I was using a version called Fortran 95. So I might have moved on a bit since then. So what about MATLAB? I know a little bit about how it works. I think I used it once, again, a long time ago. I was mostly frustrated by it. I think it's mainly for chemical engineers, so I'm surprised it's used for robotics. But Ghinwa, maybe you can tell me more.
Yeah, so I used MATLAB actually because it has these built-in functions that helps me solve the mathematical equations that I want. And I remember I used something called CFtool that basically does all the job for you. So you just need to choose what type of equation you need, or try it really to fit your data. And then once you choose the type of equation that fits well your data, it generates all the functions and everything for you. So you don't have to build actually the function itself. So it was really easy in that term.
Okay, so has it got something built in there that can sort of like figure out all the maths behind like the trends that are in your data? Is that right? Is that what you mean by a function?
If you have a trend that you have from laboratory, yeah. So let's say whatever mass variation as a function of time, and then you have a graph for that, and you need to what's the word for it, Laura? To fit.
To fit.
You need to fit your data. You need to fit your data. So you need to fit your data. So you have a set of equations you can use, for example, a linear equation, an exponential equation, whatever. So you can try different equations, and the one that you think that fits the best your data, or really it makes sense for what you are using. So you just choose this and a tool called CFtool. And then MATLAB is going to generate the function for you rather than you making the function from scratch and try to fit your data yourself. So that was really make my life easy.
I'm with you. I thought we were talking about the same thing, but I just wanted to make sure.
Yeah.
Different disciplines use different words, same words to mean different things. I think maybe that's it's one of the challenges when you learn to code yourself. You don't necessarily know like the formal terms and things like that. That's what I've found when I've picked up something new. One of the things I think I found really useful from what Fortran does is using two coding things called loops and if statements, so like do loops and if loop. That means that you can like automate a whole load of things and like set it some sort of decision-making criteria to get your code to do what you want it to do. So if it encounters, so I was working on atomistic simulations. So say it encountered like a bond length that I'd made too short, it could tell me about it. it took some of the mindless drudgery out of it when you were trying to build your molecule. So I think we're all saying, like, you can concentrate on like the interpretation of the data, or whether that fit is a physically possible thing.
Yeah, with the like if statements as well, as soon as I found out about them, I don't think I've ever stopped using them. We've had like a couple of projects where we've had to filter out data, especially in labs, and like noisy data. Like you can use if statements to get you like, I guess, quote unquote, good data to then fit. One of our projects, like initially, one of the main tasks of it was like getting rid of the nans and the infinites, and then trying to like actually get the data so you could see a relationship, because a lot of the time if you don't actually do that, you just get like a horizontal line and like the values that just don't mean anything. So I've used if statements way more than I ever thought I would when I first like found them, and my mind just keeps on going to them all the time.
Good to know. I find it so funny that you said nan, because you were the only other person I've ever encountered that says nan rather than not a number.
I say that too. I say that too. Like in Python, I think I've seen it like too many times come up with like an error message. This is not a number. This is a nan.
Oh.
Yeah, when your maths has done something that's just not physical, and the equation's like, I don't know what that is. You just get a whole page of not a number.
Yeah.
So I guess that sort of explains one of the benefits of learning to use these languages. I mentioned it can take some of the drudgery out of it. You mentioned that you can use it to filter things, so it can make things a lot easier for you.
Yeah, because in chemical engineering also we need to use it, or I need to use it just to set boundaries actually for my functions, because sometimes, for example, the function cannot be, let's say, negative. So you need to filter all that data by using if statement, and it's quite funny. So it get in my mind so deep. So whenever I want, for example, to go and do some shopping, I will be like, if the price is, if not, or if this sandwich is, if not, and then just crazy.
You spend your entire time shopping writing logic statements in your head.
Exactly. I can't get rid of it actually. And my daily life and daily tasks, just funny.
I love it. I think I do some of that in my writing as well. I've noticed I'm far more likely to write if and then in a sentence rather than just using one of those words.
Mm.
I'd sort of alluded to some of the stuff I did in my PhD, and I feel like I should explain it in a bit more detail to help demonstrate some of the benefits. So I said my PhD was computational chemistry, and the starting point there is to build your molecule on your computer, which usually involves using coordinates, so XYZ, Cartesian coordinates. And there is software that can do this for you for fairly straightforward, well-known molecules. But I wasn't working on those. I was working on some really novel, complicated ones. They were polymers, and they had maybe 100 atoms or so in each monomer. And they had all these, not unphysical linkages going on, but things that you wouldn't tend to see very often. So I had to figure out a way of building them. And then once I built them, I had to explain to the software that was going to run the molecular dynamics simulations. I had to explain to it what my molecule looked like. So I had to tell it which atom was bonded to which, and then where all the angles were between the bonds. And I could have done that by eye and written a very long list, but there's no guarantee it would have been correct. And it probably would have taken me days to do just one molecule, and I had 15 molecules in my simulation box. I thought of a way of writing some code in Fortran. I didn't actually know it was going to work. I just had an idea of how to do this algorithm using all of these if statements and loop until it had gone through my list of the bonds that I'd written and it written down all the angles and various other things for me. So that's my example of how coding made my science easier and allowed me to focus on the outcomes of the simulations and building the simulations. But what about you guys? Emma, I'm intrigued by your robotic chess playing arm.
Yeah, well, it's very much early stages of development right now, because there was people who were working on the arm last year. They kind of got it to recognize where it was in 3D space. A part of what I'm working on, because we have a problem as like a team when we think about all the stuff we have to do. Every single time it gets more complicated, and we're like, okay, let's try and focus on the simplest of things we can think of right now, and then we'll see where we go after that. And so we're working on actually trying to get the arm to move to pick up the pieces, which sounds easy, but then when your pieces could be different sizes, it's like the arm's going to knock some over eventually. And so we're trying to figure out what like function is best for the arm to pick up the pieces. and how we can actually make that efficient, because we don't want a chess piece to take 5 minutes to be took in a game. It's a bit too much thinking time for the opponent. And so that's what like my subgroup is working on. It's been really easy to visualize how the arm is working by using MATLAB. And there's like a robotics like a package that helps you. There's always like these limitations which go on because the arm has loads of joints. And so those have been pre-coded the year before. And so when we run something, we can see if that path is going to work, because it like visualizes it, which is something that's like borderline impossible to do without code. Because we're working on getting the piece to be picked up and then moved back, it's also trying to understand how to get the arm to recognize what piece it is. And so we have different parts of that project who are working on playing the game of chess, which is a completely separate thing, and then actually recognizing where the chess piece is on the board and like what it's taken up. I think it's quite a big task, but it's been really fun just trying to like think about it and work on it, because I'm on physics and a couple of my friends are on it doing physics, but there's also a few electrical and electronic engineers, and we all think about the same problems in a different way. And so they might say something and we're like, oh, wait, that's actually a really good way to think about it that we didn't think of. Even just being in that environment with engineers and physicists is really useful for a problem that like helps us like actually optimize the code, because there's so many ways you can do things in coding. Sometimes it's not always obvious which one's actually going to be the best one. And so a lot of my coding experience has been just like staring at a wall and trying to think about what's actually best, and then I'll give it a go, and then maybe it works, maybe it doesn't.
Yeah, that sounds about right. So can the robotic arm, can it see the pieces? Has it got a sensor?
No, it has a camera. And so there is like an idea for like the people on the computer vision squad, is what they're known as in the group, is like, although I think they don't want to do this, but it's doing like QR codes like beneath the chessboard, so that when it picks it up, it can read the QR code which corresponds to a piece, and then that is how it gets recognized. There's loads of ways we could do. That's like a process which we're trying to do, but first of all, I think they're working on like getting the camera to recognize when something's blocking a square, so it means there's a piece there, and then they're going to work on how you recognize the specific piece. But there's so many ways you could do it. You could do it with some form of infrared camera labeling, or there's loads of ways, but that's like me talking about physics, because we're talking about picking up the pieces as well, and all of the physicists on the team were like electromagnets, and everyone else was like, no.
Yeah, I imagine it having like a little nipper thing on the end of it, so it sort of physically pinches things to pick stuff up. I mean, that's a bit too simplistic. I quite like the idea of using magnets, but I guess you need to make sure it's gotten close enough to the right piece to pick it up and not pick up the wrong thing.
Yeah, I mean, I think that was a bit of a joke among the physicists at the time. On the arm, there is like a hand which can pick it up, but we also have to figure out how the hand, which is like the two like pincers, I guess, how we even code that to pick it up, and how like much pressure we use and everything like that. But like right now we're all thinking, it's a year-long project. That is a problem for future us.
Ghinwa, you mentioned that you got a job as a result of learning to code, and that sounds really useful. Getting paid to code.
Yeah, that's very true. Actually, it was a positive point on my CV that I do coding, but at the same time I understand the experimental side of stuff, because usually people are either in experiments and they don't want to know anything about coding, or they are in coding but they're not very much into experiments, and linking both experiments and coding is very useful, especially in what I do. So you have always to validate what you're coding and modeling in the lab and see if it really makes sense.
I think I understand what you mean, because you can see the problem from two different points of view, can't you? You can see like how you would code this thing and what the data may look like. So it sort of gives you more insight beyond just doing the experiment and seeing what comes out of your chemical engineering rig at the end.
Yeah, I mean, in your case, Laura, you did only modeling, so you didn't have to validate anything in the lab, didn't you?
It was modelling polymers that had been designed by chemists in their lab. So there was a little bit of making sure that it did actually have the same properties as the polymers that were made by the chemists.
I see. So there's that link, because in my case, even in my group, whoever's doing modeling, they just make sure all the time to validate it with some experiments, because actually you can model anything. We say in mathematics, this is something I learned from my math tutor, that if you give me 3 points, I can fit you an elephant. So you can just basically fit anything, but then how do you know it makes sense? So you got to go back to experiments and to the physics behind it. But also I used coding because I need to solve mathematical equations and partial differential equations, which you cannot solve without coding actually. So that's why I used coding basically to solve these mathematical equations.
Perhaps the physicists can help me out, because I remember doing partial differential equations and ordinary differential equations in my undergrad degree in physics. And I guess they were quite simplistic. It did take me a while to get my head around them, but they were solvable by hand. So I'm guessing you're talking about some more complex interplay between different variables.
Yeah, so you're talking about a set of equations with boundary layers and with many functions to be solved all together and a boundary conditions. So you're talking about really a complex set of mathematical model that wouldn't be solved without coding.
So is this a sort of like situation where, like, imagine like a really simple chemical processing rig, if we're talking about chemical engineering. So you've got some sort of like reaction vessel with something going on inside it, and you've got stuff flowing in and out, and you've got a temperature. So you have to sort of control all those variables and then use the modeling to predict how those variables affect what comes out at the end. Does that sound right?
Yeah, that sounds right, but in a more complex way. So in my case, I need to integrate all together heat transfer, mass transfer, fluid dynamics, all together make a link to what's happening in my rig, and then produce from these physical or mathematical equations a set of final partial differential equations that change with time, change with mass, changes whatever variable you have, and then try to solve it within a boundary conditions that I set to my system.
I get it. And the boundary conditions are like, so going up to a pressure of this amount is not possible. So that's one of your boundary conditions, that sort of thing.
Yeah, there's a different type of boundary conditions. There's stuff that, for example, some mathematical equations need to be within a certain value. Some like cannot be negative, for example.
To get not a number.
Exactly. You cannot divide by 0, for example. This is a very simple example. But also you need to set your time frame if you're having any operating conditions that you cannot exceed, as pressure, as temperature. So you need to put all these data. So imagine you have all that set of conditions all together and you need to solve the problem. So it wouldn't, I think maybe you can solve it in like, I don't know, in a lifetime. You can just, be like old scientist having your board and trying to solve the mathematical equations. Maybe you would do something about it, but yeah.
Yes, if I can give like another example of like something that is a lot simpler to maybe imagine in terms of something where you'd need numerical methods and coding. So and you probably did that at like GCSE physics, when you have a pendulum and they ask you solve the equation of the pendulum, you know how you only solve it for small angles? That's because if you don't just solve it for small angles, it's a nonlinear problem. And so you can't solve that equation, like you mentioned before, by just solving it by hand. You need something else. And so when you have a problem like that, it is much easier to just use coding. It's very, very difficult to do by hand. And it seems like an easy problem. It's just like a pendulum oscillating. But even that, you'd need coding.
I'm really glad you brought that up, Clea. We actually had a computational project on a simple harmonic oscillator, but a force-driven simple harmonic oscillator. And so a part of that was trying to actually model a regular unforced simple harmonic oscillator, which if you speak to any physicist, if you try hard enough, anything is a simple harmonic oscillator.
Yeah, chemical bonds.
Is a simple harmonic oscillator.
Yeah.
A part of that project was about solving the equations of motion when you have a force system, which you physically cannot do. And so to do that, we just literally experimented how different mathematical methods work and how they best fit the results. And you use the data you have from the unforced case to find the best method, and you apply that to the forced case. And so you can use it to solve these impossible nonlinear systems in a way that actually is not impossible and actually quite satisfying to do, because you can trust your answers. It's not just oh, let's try this and see that this is probably right. Like you can actually validate that they're going to be a good answer, which is kind of impressive when you think about it.
Yeah, it's that having knowledge of the physics that's good enough to know when the thing that is being done by the computer actually makes sense.
Yeah, physics will take you so far, but then you can go further with the code, which I think is what's quite nice about it.
For me, learning how to code really helped with my confidence. Like having that insight into how these things work, or even like I know that I can't do that thing by hand because it will take too long, or I don't have that insight. But I can code something that will give me that information. Would you guys say the same thing?
Yeah, I'd say even just giving me confidence to work on a problem, but also doing coding has given me more confidence in my coding ability. I knew Python first and then moved to MATLAB for the robotics project, but I would have never dreamed of doing that if I didn't already know Python. And I was kind of babied into Python in our like intro to programming module. Having that confidence to then work on lab projects, just like writing my own thing, and then working on the robotic arm, even though it's in a different language, it's like you have that confidence built from just practicing it. And then that confidence also helps you with the actual physics behind it and the work behind it. I definitely feel like it's helped me understand stuff and actually kind of argue how I understand it better than if I didn't actually use code at all.
And I guess there's something to be said for being able to sift through a load of data, which I remember doing at various times in my life, and occasionally thought, maybe I should code this. It might make it easier. But it was a one-off thing, and I think it would have taken me just as long to code it as it would have to do it just in an Excel spreadsheet. I might be proved wrong at some point in the future.
Yeah, I've definitely had experiences where I've just didn't have a choice but to code. In my last lab, so it was a particle physics lab, so I had to deal with a data set of 9 million different events. There is no way you can do that by hand. You have to use coding, and you have to use this if statements that we mentioned earlier, and those while loops and those functions to make nice plot in order to make some sense of that data.
That's a good point. And I think so we kind of alluded to using these loops and if statements. It helps with if you've got something really repetitive to do, like I mentioned, with figuring out where every single angle is between these bonds in this molecule.
Yeah, in my case, it was a lot of filtering, which I guess we also mentioned before. So removing everything that's negative, everything that's not a number. Or in my case, I had to look at the data that was in between two different energies. So I had to just like filter those out, for example.
Yeah, and one of the things it became useful for, so the simulations I did, I fed my molecules into some software. One of the software packages did Monte Carlo simulations of them, which is where it adds a random particle somewhere into my system and then calculates the forces acting on that particle, and then essentially flips a coin to say, is that particle going to stay there or not, based on the forces, the energy in that particular instance. And you do that enough times to get what's called good statistics, statistics that represent what you would see in real life, I think is what that phrase means.
Yeah, I mean, I've done a similar thing with the Monte Carlo techniques and simulations in a project on neutron scattering. It assigned, like, you have a random number, and then depending on the probability of that neutron being absorbed by some form of attenuating material, you can actually build up a representation of that material as like an attenuating material. And so you can actually use it to apply it, which is what I did like as an extension of my project. I applied it to if you were going to use like a material as like a moderator in a nuclear experiment or nuclear, what even is the right word? Nuclear...
You could say that, nuclear reactor, yeah.
Yeah, a nuclear reactor. And you can apply it to figure out like which material will be the best as a moderator. And so by like investigating the effects of like graphite, lead or water, you can actually use the Monte Carlo techniques to get a really efficient way of trying to actually just like get the properties of those materials and actually compare them using numbers and not just like using your brain. Because a lot of the time I was like lead is obviously not going to be as good as graphite or water, and it's just kind of like actually having numbers to kind of back up what you know from wherever it is you know that information from. The Monte Carlo techniques was definitely just interesting to do.
And I guess that example of a nuclear reactor, if there's radiation going on and you can do it with a simulation rather than exposing yourself to ionizing radiation, it also is a better way of doing things like a lot of safety equipment, I suppose. Sorry, that's my background in the nuclear industry coming out.
Yeah, I did a summer project at the UKEA last summer, so nuclear fusion, and there is so much Monte Carlo going on. I didn't do that personally, but everyone around me was doing that, just figuring out what are the best materials to use in this future nuclear fusion small reactor. Nuclear fusion. It's
there's a reaction going on. It's
I
just
guess, yeah.
fusion and not fission.
Yeah. In those nuclear fusion devices that they are building.
Just makes it sound like a mobile phone, like a handheld device. Stop. It's a lot bigger. But yeah, it does. So you're right, simulations do get used a lot to do things that would otherwise be quite difficult or maybe even dangerous, I suppose. You can do experiments on a computer. I accidentally made many small suns when I was doing my simulations because I set the simulation up very slightly wrong.
You need to put the time and the effort and invest in your skill and not be afraid of being a newbie.
Anyone can learn how to code.
Yeah, a good point of that is like when I've been coding, it's been for like a specific purpose. And so all I really know about code is like, oh, can you do this, like measuring the drop law? Can you measure this, simulate this nonlinear system or Monte Carlo integration? Or can you look at a robotic arm? And like there's so much you can do with code. And it is quite scary to just sometimes think about what you know is just such a tiny like subset of all that there is. But I think knowing that you're good at what you can do is enough to give you confidence with code, because I think with other subjects, you think you need to have a really like huge like grasp on it. But with coding, you can understand it and be good at it by only knowing like this small fraction of what to do, because it's just what applies to what you're doing individually. And so you'll meet people that like seem like they know so much about the code, but then when you get to talking to them, they really just know about what they're doing and they might not be able to understand what you're doing.
That's true. I know when I was doing my PhD, there was one person in my lab, there's like 15 of us in this computer lab, there's one person that I kept asking questions of, and he's like, I don't really know this right. I'm just really good at Googling it. Clearly that's a skill that I don't possess, because I could try and Google something and I wouldn't get an answer that made sense to me, but maybe just having that person talk to me about what they'd found in Google made that different. So I guess that says something about your learning environment as well. Find an environment that works for you.
Yeah, I think a lot of the problem as well, if you have a problem with your code because it's so personal to how you wrote it, the person who has to try and understand your code to understand your problem to then fix your problem, and then you have to implement that in your code. And so the whole like learning process when you ask somebody else sometimes can even be a bit longer than just trying to learn yourself. I found that a lot, that I was actually getting more out of debugging by just trying to fix it myself, because other people would look at it and be like, I don't know what you've done here. And I'm like, oh, it's just this and this, but it doesn't really necessarily make sense sometimes until you clean it up, of course. I feel like a lot of code is just a mess before you try and actually like make it neat.
I took to putting comments in my code quite a lot, just in case my code had to be passed on to someone else who would use it in their PhD, who was sort of sharing bits of information with each other. So a comment is something that the computer or the compiler doesn't read, but the people looking at the code can read it and say, oh, that's what that section of code means. I get it. That's why that person was doing that.
Yeah, comments and doc strings for sure in the functions.
Yeah, and if you write code without commenting, I mean, is that really valuable? Because no one else can understand what your thought process was at the time.
We got told at the start of our like first module, it was like code is read more than it's wrote, so make sure you write it well. And like in that module, I think I was so perfect with how I wrote my code, but when I'm like roughly doing something in labs, it's so quick to just like assign some bad variable names which I need to fix later. But
you ever call them just like Susan or Dave or something? I remember what that means.
It's like A, B, C, D, and then you just go through the whole alphabet, and then you're like, let's start with the Greek alphabet.
It just makes sense to call your variables the thing that they actually reflect, otherwise you get very confused. Don't call them Susan, I guess. With my weird deviation to calling variables Susan and David rather than pressure and temperature, which would make more sense. I think that's probably a good place to draw this to a close. So hopefully we've introduced valued listeners to some different types of coding and how they vary from each other, and how you can use it to control something or make a robot arm do what you want it to do, or to analyze some data that you wouldn't be able to do yourself, or to simulate some atoms that you maybe couldn't do in the lab. Anyone can code, and you can find a way of learning that works best for you, whether that's finding the right environment or finding someone to ask or finding videos online, and it helps to have a goal to work towards when you're doing that coding, so you can start small and then build up your skills from there. So if you like listening to this and you want to carry on the conversation with us, you can find us on Twitter, you can leave a comment on the episode, or you can email us as well.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.